Hello there, this is Vinay. I'm a PhD student in the EC department at the Indian Institute of Science and I'm funded by the Cisco ISC Research Fellowship. In this video, I'll share with you the research I have been undertaking on broadcast algorithms for ad hoc networks. What is an ad hoc network? An ad hoc network is just a bunch of communicating nodes without any centralized infrastructure. For example, you can think of sensor nodes deployed in a field. These could be temperature or humidity sensors which form a network. Here, the edges indicate the neighbors which are within communication range of a particular node. Let us designate a particular node as the source, possibly your location. The source needs to broadcast information to all the nodes in the network. This information could be something like updating the sensing frequency for all nodes. An alternative example that you can have in mind is that of IoT nodes. Here, one might want to do some over-the-air programming of the nodes from a source node. In both these scenarios, we need lightweight, decentralized, energy-efficient broadcast algorithms. A naive algorithm for broadcasting is flooding. Let me explain it using this small graph. Here, the yellow node is the source. Every node transmits the packet whenever it receives it. Let us see flooding in action on a larger graph of 100 nodes. Here, all the yellow nodes are those that receive the packet and have transmitted it, and all the red nodes are those that have not received the packet. Notice here that there are lots of unnecessary transmissions in the regions where there is a high density of nodes. Such transmissions consume energy. For the scenarios that I mentioned before, energy has to be used optimally and hence this is not a viable algorithm. An alternative that has been proposed is what is called as probabilistic forwarding. Here, every node on reception of a packet of information tosses a coin and transmits it if the coin lands heads. To illustrate in our example, suppose one of the nodes tosses heads and the other tosses tails. The node which tosses heads further forwards the packet. Subsequent receptions of the same packet are neglected. Let us look into a simulation of this algorithm. Here again, the yellow nodes are those that received the packet and forwarded it. The blue nodes are those that only received the packet but did not forward it. And the red ones are those that did not receive the packet at all. While this algorithm does decrease the number of transmissions, reception of a packet is not guaranteed. In order to improve upon the number of nodes that receive the packet, we introduce coding along with probabilistic forwarding. Let us see how this works on our toy example. The source encodes the single packet into two packets and forwards it. Now, carrying out probabilistic forwarding as before on both the packets independently gives a higher chance of all the nodes receiving the information from the source. More generally, the source encodes the k data packets that needs to be broadcast into n-coded packets. The code used is such that the reception of any k out of the encoded packets by a node suffices to retrieve the original information that the source intended to send, that is the data of the k initial data packets. We have observed that on most well-connected graphs, such as the grids, lattices, and random geometric graphs, the number of transmissions actually decreases as compared to the case when no coding is used, while ensuring that a large fraction of the nodes receive the broadcast. Thus, in essence, we have come up with an energy-efficient broadcast algorithm. To know more about this and other works of mine, take a look at my publications. Thanks to 3Blue1Brown for the man-name library which helped me make this video.